Here is the full story in one complete piece. Joseph Smith was not supposed to be the man who saved the Spitfire. That was someone else's job. That job belonged to R.J. Mitchell, the brilliant engineer who had designed the Spitfire in the first place, who had poured his health and his final years into making it fly. But Mitchell died in 1937, taken by cancer at the age of 42, and the Spitfire he left behind was already becoming a legend before it had even seen real war. Smith stepped into the empty chair. He was a quiet man from Birmingham. Not the kind of person who made rooms go still when he walked in. He had grown up in the kind of household where you learn to work with your hands before you learn to have opinions, where you earned the right to speak by first doing something worth speaking about. He had started his career as an apprentice at the Austin Motor Company, fixing motors, learning tolerances, developing the kind of patience that only comes from spending your days inside problems that do not care how tired you are. He moved to Supermarine in 1921. He became chief draftsman. He sat at the shoulder of R.J. Mitchell for 16 years, learning the man's philosophy, absorbing his thinking, watching the way a great designer approached a problem not by asking what was possible, but by asking what was necessary. When Mitchell died, Smith was appointed chief designer, and the entire aviation world looked at the empty chair, and then looked at Smith, and waited to see what would happen next. What they expected was maintenance. Someone to keep the lights on. Someone to protect what Mitchell had built without being foolish enough to think he could add to it. Smith had different ideas. He just did not announce them. The Spitfire in 1937 was already remarkable. It was fast, elegant, and responsive in a way that made pilots feel like the aircraft was an extension of their own body rather than a machine they were operating. But Smith understood something that most people around him were still working out. A fighter aircraft is not a monument. It is a conversation with the enemy, and the enemy does not stop developing. He saw clearly that the Spitfire's existing engine, the Rolls-Royce Merlin, had limits. Beautiful limits, hard-won limits, but limits nonetheless. And across the channel, German engineers were pushing their own designs forward with the urgency that war produces. Smith began thinking about what came next. The answer was already sitting at Rolls-Royce, waiting to be properly used. It was called the Griffin engine. Where the Merlin had a displacement of 27 liters, the Griffin had 37. It was a V12, liquid-cooled, and it produced a level of power that the Merlin could not match. Engineers at Rolls-Royce had designed it originally for Fleet Air Arm aircraft, the heavy carrier-based planes that needed enormous power at low altitudes. But Smith looked at that engine and saw a future for the Spitfire that most of his colleagues thought was wishful thinking. He formally proposed fitting the Griffin into the Spitfire in 1940. The timing was difficult. Britain was fighting for its life. The Battle of Britain consumed everything, every hour of manufacturing, every engineer, every test pilot. Lord Beaverbrook, the Minister of Aircraft Production, made a decision that made complete logical sense given the crisis: stop developing the Griffin and concentrate every available resource on producing the Merlin, which was already in the aircraft, already in the air, already fighting. Smith's proposal was shelved. He waited. He kept developing. He kept the idea alive in the drawing office, in conversations, in the careful accumulation of design work that would be ready when the moment came. And the moment did come. By 1942, with the immediate emergency of the Battle of Britain past and German performance threatening to outpace British fighters, the Griffin Spitfire project was revived. The first Griffin-powered Spitfire flew on the 27th of November 1941, and when test pilot Geoffrey Quill climbed out of it, his report was enough to make the skeptics quiet for a moment. The aircraft was spectacular. It was also terrifying to fly. This was the problem that Smith had not yet solved, the problem that would define the next several years of his working life, the problem that would eventually lead people to call his proposed solution stupid before they admitted it was genius. The Griffin engine produced power of a kind that the Spitfire's airframe had never been asked to manage. When a pilot opened the throttle on a Griffin-powered Spitfire, the torque produced by the spinning propeller was so violent that the aircraft tried to swing hard to the right on takeoff. The force involved was not subtle. It was not a handling characteristic that an experienced pilot could manage with a small adjustment. It was a physical assault on the aircraft's direction, a brute yaw that demanded constant correction from the pilot at the exact moment when the pilot had the least mental bandwidth to spare, the moment when the wheels were leaving the ground, when the aircraft was transitioning from a ground vehicle to an airborne one, when speed and altitude were both still low and the margin for error was essentially nothing. Making it worse was a particular cruelty of engineering history. The Griffin's crankshaft rotated in the opposite direction to the Merlin's. This meant that pilots who had spent years training on Merlin-powered Spitfires had built instincts that now worked against them. The muscle memory that had kept them alive was reversed. Everything they knew about correcting torque on takeoff was wrong in the Griffin variant. They had to unlearn safety in order to fly the new aircraft, and unlearning safety is not something a human being does quickly or comfortably, especially while simultaneously managing 2,000 horsepower trying to drag the nose sideways into the ground. The engineering teams tried everything reasonable. They enlarged the vertical stabilizer, the tall fin at the rear of the aircraft, to give the rudder more authority over the yaw. It helped. Not enough. They adjusted the rudder's geometry, gave the pilot more mechanical leverage to fight the torque. It helped. Not enough. They explored trim adjustments, different propeller blade configurations, modifications to the way the engine's power was delivered. Every solution they tried was a patch that reduced the problem without resolving it. Smith was watching all of this. He was calm in the way that people are calm when they have already decided what the answer is and are waiting for everyone else to catch up. His answer was 2 propellers. Not 2 engines. 1 engine. But 2 propellers, mounted on the same shaft, spinning in opposite directions simultaneously, one set of blades turning clockwise and the other turning counterclockwise, their opposing rotations canceling out the torque that had been making the aircraft nearly impossible to control on takeoff. The physics was straightforward. If the torque from a clockwise spinning propeller pulled the aircraft in one direction, then adding a counterclockwise propeller generating equal and opposite torque would result in 0 net torque. The aircraft would sit straight. The pilot would only have to fly. The engineering, however, was not straightforward at all. To drive 2 propellers from a single engine, spinning in opposite directions on the same shaft, required a gearbox of extraordinary mechanical complexity. The tolerances were almost impossibly tight. The system needed to transfer thousands of horsepower through gears into 2 coaxial shafts rotating against each other, reliably, under the vibration and stress of high-performance flight, at temperatures that varied enormously between the ground and high altitude, without failing. In peacetime, with unlimited time and resources, this would have been a serious engineering challenge. In wartime, with production lines already committed, with mechanics in the field who needed to maintain whatever flew, with the ever-present demand that everything be simple enough to actually work under combat conditions, the challenge was enormous. When Smith presented the contra-rotating propeller concept more formally, the reaction was not encouraging. There were men in that room who had spent their careers making aircraft. They had opinions. The gearbox was too complex. The weight penalty would reduce the very performance gains the system was meant to unlock. The reliability risk in combat conditions was unacceptable. Development time was a luxury Britain could not afford. The word that circulated was pointed and brief: stupid. Smith kept drawing. The solution he developed with the Rolls-Royce engineers, who came to share his conviction even if they shared his skepticism about the timeline, used 2 pinions of different sizes. The front pinion was smaller than the rear. The difference in size drove an additional idler gear. The idler gear reversed the rotation of the second propeller shaft relative to the first. 2 coaxial shafts, spinning in opposite directions, driven by a single engine. 2 sets of propeller blades, one spinning each way, their torques eliminating each other completely. The mathematics was elegant. The machine that embodied the mathematics was a masterpiece of precision manufacturing. It required new techniques, new tolerances, new training for the engineers who would build it and the mechanics who would maintain it. It was not simple. But simple, Smith understood, and Mitchell had taught him this, was a description of the outcome, not the process. The outcome needed to be simple for the pilot. The engineering behind it could be as complex as necessary. The first aircraft fitted with the contra-rotating propeller system flew, and the pilot climbed out and said something that no pilot had said about a Griffin Spitfire before. It was docile. Not fast. Not merely powerful. Docile. Controllable. The thing that had been a barely managed explosion of torque was now an aircraft that sat straight, that responded to input rather than fighting it, that gave the pilot back all the mental and physical energy that had previously been consumed in simply keeping the nose pointed in the right direction. And with that energy freed, with the torque neutralized, with the full output of the Griffin engine now flowing cleanly into thrust rather than fighting itself against the airframe, the aircraft began to do what Smith had always believed it would do. It went fast. The Spitfire variants that followed the contra-rotating propeller development reached speeds that seemed almost incompatible with the aircraft's origins. The Mk-14, powered by a Griffin engine in its advanced two-stage supercharged form, could climb to 20,000 feet in just over 5 minutes and reached a top speed of 446 miles per hour. But the later versions, the ones carrying the fully developed Griffin engines with contra-rotating propellers, pushed the boundary further still. Aircraft in the Spiteful line, which carried the Spitfire's DNA in everything except name, reached 494 miles per hour in trials with full military equipment. The figure of 470 miles per hour, achieved by Griffin-powered Spitfire variants with contra-rotating propellers, was a number that would have seemed like fiction to the men who had built and flown the original Spitfire just a few years earlier. Piston-engined. Propeller-driven. 470 miles per hour. The jet age was arriving while all of this was happening. The first jet fighters were already flying by the time the Griffin Spitfire variants were reaching their peak performance. The engineers of the future were pointing toward turbines, not pistons. There was a sense in some quarters that everything being done with the Spitfire and the Griffin was a beautiful irrelevance, an impressive ending to a chapter that was already closing. This view irritated Smith, but he did not waste time arguing with it. He kept his head in the drawing office and kept developing what was in front of him, because the war was not over, and the aircraft flying the war were Spitfires, and the pilots flying those aircraft needed every advantage he could give them. The contra-rotating propeller system found its most essential application not in land-based fighters but in the naval Seafire, the carrier-based version of the Spitfire that operated from the decks of British aircraft carriers. Carrier operations are among the most dangerous activities a pilot can perform. The approach to the deck happens at low speed and low altitude, with very little margin for error. A go-around, the maneuver where a pilot decides not to land and applies full power to climb away and try again, is the moment of maximum danger, because it requires maximum power at the exact combination of conditions where torque is most destructive. Full throttle, low speed, low altitude. The old single-propeller Griffin in that situation was a machine that wanted to kill the pilot. With contra-rotating propellers, the Seafire could apply full power cleanly. It would climb when asked to climb. It would fly straight when asked to fly straight. Pilots who had dreaded the go-around were given back control of their own survival. Smith never made speeches about this. He did not have a gift for the dramatic gesture. He was a draftsman's personality, a man who understood that the work existed in the details, in the millimeter tolerances, in the ratio between the two pinion gears, in the decision to route the magneto drives through the propeller reduction gears rather than separately, which reduced the engine's frontal area and kept it fitting inside a Spitfire nose that had not been designed for something this large. Every decision was a problem solved. Every problem solved was an aircraft that flew better. Every aircraft that flew better was a pilot who came home. He led Supermarine's design office through 24 marks of Spitfire in total. 24 iterations of an aircraft that began as Mitchell's and became, in all the ways that matter during a war, Smith's. Not because Smith claimed it, but because he was the one who kept finding ways to make it better when everyone around him had decided it was already as good as it could get. After the war, he moved the company's work into jets. He designed the Supermarine Attacker, one of Britain's early naval jet fighters. He worked on the designs that would eventually become the Supermarine Swift, a jet that broke the world speed record in 1953, covering a measured course at 737 miles per hour. The Swift was as different from the original Spitfire as a racehorse is from the cart it was born next to, and Smith had drawn it. He was proud of it. He died in 1956. He was 58 years old. The book written about his career is called Spitfire's Forgotten Designer. The title is the whole story, in 3 words. The men who took over from a genius and spent 19 years proving that the aircraft the genius built had more in it than the genius had time to find, and who solved a problem that experienced engineers called unsolvable using a piece of mechanism that experienced engineers called stupid, and who gave pilots control of their aircraft in conditions where they had previously been fighting just to stay upright, was forgotten. Not by the pilots who flew the aircraft he developed. Not by the engineers who understood what the contra-rotating gearbox had actually required to build. Not by anyone who has ever looked at the speed figures of the later Griffin Spitfire variants and asked how a World War II fighter aircraft reached 470 miles per hour on a piston engine and come away understanding what it cost to get there. Forgotten by history in the way that history always forgets the people who defend and develop and improve, the people who inherit brilliant things and make them better through patience and refusal and the particular courage it takes to keep drawing when the room has already decided you are wrong. Mitchell designed a fighter. Smith built the aircraft that fighter became. And the aircraft that fighter became could reach 470 miles per hour, could climb away from a carrier deck without killing its pilot, could outrun almost every piston engine machine that shared the sky with it, because a quiet man from Birmingham looked at a problem that had defeated everyone else and decided that two propellers spinning in opposite directions was not a stupid idea. It was the only idea.